Alright, so in this video we're going to discuss the third theorem for Laplace transform, which is called as the second shift theorem. So previously we have discussed the first shift theorem, so the idea is going to be pretty much the same. So you're going to use the second shift theorem when you have function involving products. But for first shift, when one of the function involved is an exponential. But for second shift theorem, it is going to be used when one of the function that is being multiplied is a unit step function. So this is the function right here. So remember, I've explained this to you before about the unit step function in the introduction of Laplace transform. So the second shift theorem states that if a is a constant and Laplace of f of t is equal f of s, then if you were to Laplace a product of unit step function with any function, so the outcome is going to be exponential of negative as multiplied by f of s. Alright, so when we are going to use this theorem right here for cases like this. For example, let's say if I have Laplace of ut minus 2, so multiplied by t square. So here, because of the function ut minus 2, which is a unit step function, and it's a product with the t square, automatically this is going to be done by using first shift theorem. And second example, let's say if I have Laplace of exponential t multiplied by ut plus 1, so this can also be done by using second shift theorem. Actually, when you come across cases like this, for which you have both exponential and unit step, there are two ways of finding the Laplace transform. So if you consider the fact that you have exponential, so you can use the first shift theorem. And if you consider the fact that you have a unit step function of ut plus 1, so you can use the second shift theorem. So no matter what theorem do you use, at the end, the answer is going to be exactly the same. So you have choice here if you come across something with exponential and unit step. So you can either use first shift, you can also use second shift. So which one? So pick any theorem that you are more comfortable with. Alright, so now let's have a look. So what do you need if you wanted to find the outcome of Laplace transform using the second shift theorem? Alright, so first of all, what you're going to do is from the unit step function, you're going to identify what is going to be the value of a, and the value of a goes right there, so as the power of the exponential. And anything else in the function that is not the unit step function is going to be considered as f of t minus a, and what you're going to do with that is that you are going to change that to f of s, and actually there is only one way to get f of s, and that will be from f of t. And what you have to do with f of t is that you have to Laplace transform that, and of course converting from f of t minus a to f of t, so this is just going to be some simple algebraic manipulation that I'm going to explain to you later. Okay, if you notice right here, so the fact that this theorem right here is when you have a function of ut minus a. So what happens when your function is in term of u of t plus a? So the thing is that, so these two, they are always going to be the same. So if this is ut minus a, this is also going to be f of t minus a. They are always a match. So if I have ut plus a, of course, this is also going to be f of t plus a. And what happened on the other side is that, so if this is minus and this is minus, the power of exponential is also going to be minus. So that is why, so when I have a plus and plus right here, I'm going to end up with exponential of positive as multiplied by f of s. And of course, so in the final exam, in the appendix, there is only one theorem given, which is the one at the top right here. But you have to know how to manipulate your theorem when you have a different case of positive and negative. Okay, so now before I start with my first example, so let's have a look. How do we convert from f of t minus a from f of t? So this is going to be a very important step. So if you don't know this, you will have problem trying to find the Laplace transform by using second shift. So actually this is a very simple algebraic manipulation, but you have to understand really well so how it works. So let me start with the first example. So here I have a function of f of t plus 1, which is equal t squared plus 2. So the idea is that I have to think, how do I convert from t plus 1 to t? Because later I'm going to be converting this to f of t. So we are going to convert from f of t plus 1 to f of t. So the idea is that, how we're supposed to convert t plus 1 to t is we are going to add a constant. So how do I get rid of the plus 1? What I have to do is I'm going to minus 1. So that is why. So in this function, what I'm going to do is every single time I come across t on the right hand side of the function, so instead of using t, so that will be replaced by, so this is going to be t minus 1 square plus 2, right? So the idea is, so the t's are going to be changed to t minus 1 because I wanted t plus 1 to become t. Okay, let me show you one more in order to become clearer. So let's have a look over here. So I have f of t minus 2 and it's going to equal exponential of t minus 2t. For this case, I have t minus 2 and I wanted to convert this to f of t. How do I get rid of the minus 2? I have 2 plus 2. So therefore, so there goes my t. I have 2t function right here. So when I convert this to f of t, so what I need to do is plus 2 to all the t's. I'm going to end up with exponential of t plus 2. So put a bracket around. So minus 2 again. So I'm going to have a bracket of 2 multiplied by t plus 2. So that's it. So that's a very simple idea. Okay, so the last one. So I'm going to be converting this to f of t as well. So I have t minus 1. I'm going to be converting this to t again. So I get rid of negative 1. I have to add 1. So let me highlight all the places for the t's. So therefore, so my function is going to be delta. So put a bracket around the t. So it's going to be plus 1 for this case. I'm going to have t plus 1 plus 1. And then here I'm going to have for the exponential, put a bracket around. So t plus 1 minus 1. So if I were to simplify this, I'll end up with delta of t plus 2. So plus exponential of t. So it's going to be as easy as that. So that will be the idea. So how do we convert from f of t minus a to f of t? Okay, so next, let's have a look at the example. So now that you have understand the idea, so I'm going to show you two examples. I'm going to start with a very simple one, which is the one right here. So let me put the theorem on top so we can compare them. No, that is not what I wanted. Right, so let's put a theorem on top. So Laplace of ut minus 2, f of t minus 2. So that is going to equal exponential of negative es multiplied by f of s. Okay, now I'm going to separate this, the unit step and the rest of the function. So from here, from the u, I can identify right away my value of a is going to equal 3. And according to the theorem, so this is going to equal exponential of negative 3s multiplied by f of s. That will be the final outcome. So now all I have to do is figure out what is going to be f of s. And anything else aside from the unit step function, so that will be a function of f of t minus 3. Remember, so this two, they has to be a match. If this is t minus 3, this is going to be t minus 3 as well. And for this case, it's going to equal t squared, and I'll be converting this to a function f of t. Remember what I mentioned just now? Here I have t minus 3. I'm going to convert that to t. So what I have to do is I'm going to add 3 to get rid of the negative 3. So therefore my function is going to be t plus 3 to the power of 2. And because later we have to Laplace transform this, so you have to simplify and expand if you have something like this. So then we will end up with t squared plus 6t plus 9. And I'll be converting this to f of s, which is going to be the Laplace of each of this term right here. You only have to apply the linearity theorem and Laplace them individually, for which we'll end up with 2 over s cubed plus 6 over s squared plus 9 over s. And of course, that is not yet the final solution, because remember, this is the final solution. So I have to write that Laplace of ut minus 3 multiplied by t squared. So that is going to equal exponential of negative 3s, and put a bracket around and copy down all the function f of s. And the last one is going to be 9 over s. Okay, so that will be the Laplace of this product of unit step function right here. So as long as you know how to convert from f of t minus a to f of t, so this should not be a major problem for you. Alright, so this is actually a final exam question. So I purposely picked up this question. So this is from semester 1, 1920. So it's a very recent one. Okay, first of all, so here, in order to solve for this, in order to find the Laplace transform of this, for Laplace transform we don't call solve because we don't solve it, we just find the Laplace transform. So I'm going to have to apply 3 theorems. So the first one is going to be regarding this. Okay, because of the plus right there, I'm going to apply the linearity theorem. Okay, so I can write that here. I'm going to have Laplace of ut plus 2. So multiplied by t squared plus 3t minus 1. So that is going to be my first Laplace transform, plus Laplace of exponential of t multiplied by cos of t. Why is that so? Because this over here, 1 over secant of t, so that is going to equal cos of t. So 1 over cos of t, so that is cos of t. Alright, so now I have separated them by using linearity theorem. But if you notice right here, so for each of these 2 terms right there, so I'm going to have to apply different theorems. So this one, because of a product and one of them involves a unit step function, so that will be second shift theorem. And for the second Laplace transform, because I have an exponential right there, so this is going to be first shift theorem. So what you have to do when you come across cases like this is that, so do them individually, then only combine them at the end of the calculation. So now let's start with the first one, which is the second shift theorem. So then put over here by second shift theorem. Okay, so from this function right here, straight away we can identify a is going to be a value of 2. So my function of f of t plus 2, remember this 2 is a match, is going to equal t squared plus 3t minus 1. And I have to convert this to f of t by adding a minus 2. So everywhere there's going to be t minus 2 square plus 3 multiplied by t minus 2 and minus 1. And simplify this, so for which you will get t squared minus 4t plus 4 plus 3t minus 6 minus 1, and I'll end up with a t squared minus t, and I'll end up with 4 minus 7, that is going to be a negative of 3. Alright, so what I'm going to do next is I'm going to find the Laplace transform of that by converting this to f of s. So I'll have 2 Laplace transform t squared minus t minus 3, and that will be 2 over s cubed minus 1 over s squared minus 3 over s. That will be the outcome, right? So that is going to be one part of the calculation. So which is the first term, to Laplace the first term. And I'm going to work on the first shift theorem. Right, so here I'm going to use the first shift theorem. I identify the fact that a is going to equal 1 and f of t is going to equal cos of t. And my function f of s is going to equal s over s squared plus 1. So that is the Laplace of cos of t by using the table, right, according to the theorem. So this is going to equal f of s minus 1, so which is going to be s minus 1 at the top, and at the bottom I'm going to have s minus 1 square plus 1. And remember this for this one over here, so this is not the end yet. So at the end, according to the theorem, so this is going to equal exponential of positive 2s multiplied by f of s. I'm going to write together, and I put together all the answer right here. Okay. So therefore, from my calculation, by using both of this theorem, so I figure out that, so the Laplace of the terms at the top right there, so it's going to equal exponential of 2s multiplied by f of s, which is given by 2 over s cubed minus 1 over s squared minus 3 over s, plus Laplace of the second term, so which is given by s minus 1 over s minus 1 square plus 1. So that will be the final outcome. Okay, so you will get a lot of marks for problems like this. For shift right here, So the minimum marks probably is going to be 3, or usually we'll give 4 marks for this, and this one is going to be at least 5 marks, and combining them together is going to be another 1 mark. So actually you could get 10 marks for a question like this. I can't remember what is it exactly last semester the marks is, but I think it's probably, yeah, around that. Probably it's going to be like 8 to 10 marks for this, but I think it's going to be 10. Alright, so that is going to be for the second shift theorem. So as usual, so I've actually put together the notes for this, and with the notes, so there will be exercise for you to try. I have a bunch right here that you can go figure out by yourself. This is going to be a really good exercise to test your understanding, and the solution is at the bottom right there. And these are combinations of tests and final exam questions from previous semesters. So give it a go.